Now we're going to talk about, ultimately, we're going to talk about connected components. And to start off with, I am going to write down a proposition that lets us talk about when the union of two connected sets is still connected. And this is a little bit simplified based on the version in your book, but not by very much. I think it preserves the main idea, and it's all we're going to need for our discussion of connected components in a moment. So we start with a metric space. And we're going to let E be a collection of subsets of X. And we're going to assume the following two things. First, that this is a collection of connected sets. So each E in our collection is connected. And second, we're going to suppose that there is some point X in X with a single point that's in E for all the sets in our collection. And you can put this more succinctly as the intersection over all the E's in our collection E that is not empty. So there's some point in all of them. And the conclusion is that then if the intersection is not empty, then the union over all the sets in our collection is also connected. On the other hand, the statement I've made is stronger than strictly speaking we need. So let's consider this collection of sets. We've got our red set, we've got our orange set, and we've got our yellow set. And notice that there is indeed a point in the intersection, a point that's in all of them. It's right here. So this is the picture of what's going on in our lemma. But you can say weaker things. Your book proves this lemma for this picture. Notice that any two of the sets in this collection, they intersect somewhere, here or here or here, but there's no point where all of them intersect. Or you can have a longer chain of intersecting connected sets. And notice that this is pretty clearly connected, but you've got lots of pairs that do not intersect. So the proposition is also true under some weaker assumptions. Now, you could show that this thing is connected using our proposition, using induction. First, the first two who are connected, and then the next one, and then the next one, and then the next one. But I think we'll leave that to the interested student. And the proof is fairly straightforward. So we're going to take your characterization from the homework of what it means for a set, for a subset of a metric space to be connected. Let's let U and V be subsets of X, be open, disjoint. So U intersect V equals the empty set, and we'll say the union of all the E's is contained in U. Actually, I'm going to call them V and W just so that they stop looking like our union symbol. And you proved on the homework that if you've got two open sets that are disjoint and your set is contained in their union, well, then your set is connected if and only if it always has to be in one of them. So then X is in each of these E's, so it's in all of these. So X is in V or X is in W. And without loss of generality, you can just change their names. X is in V. Now, if E is in our collection of connected sets, then E is connected. And E is a subset of V union W. So since V and W are disjoint open sets, that means either E is a subset of V or E is a subset of W. But X is not in W since X is in V, and there's nothing in both of them. So E is a subset of V. And this is true for all of the E's in E, so the union is a subset of V. So our union is connected. So now we are going to define something called a connected component. So we let XD be a metric space. and we're going to pick a point in our metric space. And then this set, this is the union of the set of all subsets of X that contain our point X and are connected. We call that the connected component of X. That contains the point X. And there are two things I would like to point out to you about connected components. The first is that we're taking a union of a bunch of connected sets that all contain X. So by the proposition we just proved, if I'm going to name it C sub X is the connected component containing X, since it's a union of connected sets that all contain X, then C sub X is connected. And second thing I want to point out to you is, remember how we defined the interior as the union of all the open sets inside of a set, and thus the interior is the biggest open set inside of a set? Well, the connected component is sort of like that. It's the union of all the connected sets containing X. So it is the biggest connected subset of X that contains X. So by definition, if X is in E and E is connected, then E is one of the things we unioned up to get the connected component containing X. It must be a subset of C sub X. Now I would like to prove a partition about connected components containing different points. So with all the notation as before, let's let X and Y be 2 points in our metric space. Then either the connected component containing X and the connected component containing Y are disjoint. There are no points at all in both of them, or they are the same set. And the proof of this is pretty quick. So let's suppose they are not disjoint. They've got at least one point in common. Well, let's give it a name. then we've seen that the connected components are both, in fact, connected. So they are connected sets containing Z. So we have that C sub X is a subset of C sub Z because the connected component containing Z is the union of all the connected sets containing Z, including the component containing X. So and this is, of course, also true for Y. So we have that Y is in C sub Z. C sub Z is connected. Same argument again. It's just the maximality argument. So C sub Z is a subset of C sub Y. So we've got C sub X is a subset of C sub Z, is a subset of C sub Y, and exact same argument with X and Y reversed. So they must be equal. So let's summarize a little bit of what we have said about connected components. Let's let script E, that'll be the set of all connected components. That's the set of all subsets of X where you can write them as the connected component containing X for some, for at least one, often several, but at least one X in X. Then two things we can say. First thing is that E is what we call a partition. And in this context, what partition usually means in mathematics, it means something a little funny when you're talking about Riemann integrals, but in the rest of the mathematics, it means that each X in X is in exactly one of the connected components, exactly one of the sets in our set of connected components. And that's pretty much what we proved before, or at least it's a trivial consequence. I won't write down anything more about that. Furthermore, and I will write a sentence or two proving this, if D is a subset of X is connected, then D is a subset of E for one of the connected components. And if D is anything except the empty set, then D is contained in exactly one connected component. And is disjoint from all the rest of them. And let me write out the proof. Obviously, if D is the empty set, it's contained in all the connected components. Otherwise, if D is not the empty set, let X be in D, then D is a connected set containing X, so by definition it must be one of the things we unioned up to get C, to get the connected component containing X. So we've got D is in C sub X, and we have that if D intersected with any other connected component is not empty, then, well, passing to CX certainly isn't going to make it become empty, so CX equals CY. So what that means that if any connected component that is not disjoint from D is secretly the one we started out with, so D must be disjoint from all the rest of them. And that completes the proof. Let's bring Arkansas and Hawaii back. Arkansas is connected, so this one has one connected component. And it is the whole space. Hawaii, or at least as much of it as fit on this map, has 6 connected components. Here they are: 1, 2, 3, 4, 5, 6 connected components. And they are exactly what your eye thinks they should be. But even in a very strange metric space, and there are strange metric spaces out there, you're going to look at one on the homework, you can still do this thing. You can still break the metric space up into a bunch of connected pieces. Now let's talk a little bit about connected sets and closures. So here is a slightly simplified version of proposition 5.6.11. So we start as usual with the metric space. And we're going to take a subset of our metric space. And let's suppose it is a connected set. Then the conclusion is that the closure of E is connected. And to prove this, it's a pretty quick proof. Let's let V, W, subset of X be open, disjoint, and we're going to assume that the closure of E is contained in their union. And as you saw on your last homework, the closure of E is connected if and only if these 3 assumptions imply that the closure of E is in either V or W. So let's do this. Observe E is contained in the intersection. So, and E is connected. So we can conclude E is contained in V or E is contained in W. And without loss of generality, that is often abbreviated WLOG. Without loss of generality, E is contained in V. That means let's just let V be the name of the one that contains E and W be the name of the one that does not. Then X minus W is a closed set. It must be closed. W is open. E is a subset of X minus W, and the closure of E is the smallest closed set containing E, so we can go ahead and conclude that the closure of E is contained in X minus W. But by assumption, the closure of E is contained in V union W. So, and we've seen that nothing in E is in W, everything in E is in either V or W, so we must have that the closure of E is contained in V. And this is true for all such V and W. So E is closed. So, sorry, closure of E is connected. And that is all there is to that. And as an immediate corollary, we have that all the connected components of metric spaces are closed. And the proof, it may be obvious to some of you, but let's write it out. Let E be a connected component. If it is empty, then of course it is closed. The empty set is always closed. So let's assume that E is not empty. So there's some point X in E. Then E is the union of the set of all subsets of X that contain our base point X, and D is connected. And also we've seen connected components are connected. E is connected. So a closure of E is connected. So we have that closure of E is contained in this union. which is equal to E, and any set is contained in its own closure. So closure of E is equal to E, so E is closed by proposition 5.3.9a. That's all there is to that. Now, we've seen that connected components are all closed, and we know that a set is disconnected if and only if it has a subset that's both closed and open. So you might be tempted to try to prove that connected components are always open. Well, this fails, and one of the problems that may show up on your next exam is that I'll ask you to give an example of a metric space whose connected components aren't all open. Some of them are not open. So I'm going to write down a proposition that gives two sufficient conditions for a set to have all of its connected components be open. So the first thing we're going to note is that if XD has finitely many connected components, they are all closed. They are all open. Part B is a little bit more interesting. So let's suppose that for all x in X, there is an open set G that contains X and such that is connected. Then we have that all the connected components are open. So if you're trying to construct a space where one of the connected components is not open, you're going to have to come up with at least one point in this space where every open set containing it is disconnected, and in particular, or every little ball around this point is disconnected. And let's write out the proof of this. So for part A, suppose the components there's finitely many of them, so let's just name them E1 up through En. Then if K is between 1 and N, then let's call it Fk. The idea is we're going to take all of the other components. We'll go from 1 to k minus 1, and then we'll skip k, and we'll go from k plus 1 up to n. These are both these are both EJs. This is closed because it is the union of finitely many closed sets, and it's one of the very early propositions in section 3.2 is that you can take the union of finitely many closed sets and it's closed. So then EK is everything else that is open just by definition of an open set. That's by definition 5.3.1. Then here's part B, which is a bit more complicated. Let's let E be a connected component. If it is empty, then of course it is open because the empty set is open in every metric space. So let's assume, so let's let X be in E. Let's pick a point in E. And let's let G satisfy X is in G. G is open and connected. Then G is a connected set containing X, so it must be contained in the connected component containing X, so G is a subset of E. And then by proposition 5.3.3, there is a positive radius R such that the ball centered at X of radius R is contained in G, which is a subset of E. So we've seen that every point in E, there's an open ball of it that's contained in E. So this is true for all X in E. So E is open by proposition 5.3.3 in the other direction. Remember, proposition 5.3.3 is an if and only if statement. Let's see a particular case of spaces where every set is contained in a connected open set. This is example 5.6.6. We'll end up having to do A and B. So this is actually going to be a lemma. We will end up proving something about general open sets in Euclidean space. But if X is in Rp and R is greater than 0, then the ball centered at X of radius R is connected. And let's write out the proof of this. So let's let Y be in the ball centered at X of radius R. Then let's define the function gamma sub y. Its domain is going to be this interval from this closed interval from -1 to 1, mapping to its range is RP. We'll see what its image is in a minute. by gamma sub y of t. We'll call that x plus t times y minus x. This is what gamma is designed to do. Here's x in the middle. Here's our ball centered at x of radius r. And here is our point y somewhere else. And then what we're trying to do is we're trying to let gamma map a segment, which is something we understand it's an interval in the real line, so it's connected, into our P. And that ought to be connected. It sure looks connected, and that's a connected set that goes through, that's inside this ball and includes y. And then the idea is we can keep doing that. We can draw a connected segment like this for every point in the ball. They'll all have x in them right here in the middle, and they'll pick up every point in the ball, so their union will also be connected. That's the picture of what we're trying to do. Let's work it out precisely. Then the distance from x to gamma sub y of t, we write out what the metric is in RP. You take the square root, sum from n equals 1 to p. You take xn plus t times yn minus xn. That's gamma y of t. You subtract off the xn. You do a little bit of arithmetic. You just get a t times the distance from x to y, or absolute value of t. T is allowed to be a negative number. So now we're going to go ahead and let e sub y be gamma sub y of the interval from -1 to 1. Notice that x, that's gamma sub y of 0, is in e sub y. Y that's gamma y of 1 is in EY. And since the distance from x to y is less than r and the absolute value of t is less than or equal to 1, we have that EY is contained in the ball centered at x of radius r. All right, and this interval from -1 to 1 is an interval in R, so is connected by proposition 5.6.3, and gamma sub y is continuous. You can prove that it's continuous using the epsilon delta characterization of continuity, or you can break it up into its components and see that those are all linear and so continuous. So by theorem 5.6.4, EY is connected. X is in EY for all y. So that means that the union over y in y, E sub y, is connected. But this union is the entire ball. We've seen that each y is in E sub y, so that means that our ball is contained in the union. I suppose our first inclusion is in fact an equality. Obviously an inequality. And we saw that each EY is contained in our ball. So we've got this inclusion. We've got inclusion in two directions. So the union must be equal to the ball. That must be connected. And we'll finish this video up with not quite all of proposition 5.6.16a in your book, but enough. Let's let G be a subset of RP, be open. Then the connected components of G are also open. And we can prove this just by putting together the lemma we have just proven and the proposition from the previous slide. You just let X be a point in G. Then there is a R greater than 0 such that ball centered at X of radius R is contained in G. And this is the ball defined in RP. So we've seen that this ball is open and connected by the proposition that's not numbered that says that if every point has a connected open set around it, then all the components are connected, the components of G are themselves connected.